Okay, hello everyone. So, 8, 9 videos that tell you a little bit about what I'm going to be building on. So, after 11 months of researching the filter, it is now time to start building the first iterations of it till we get to the MVP prototype. And yes, there's still many things that we're doing behind the scenes with my co-founder and I, but we will try and share as much as we can because content is king and bullish on documenting the process because there is somebody somewhere who will want to do this one day. So might as well share him the road so that he or she doesn't have to suffer as much as what I must go through. But anyway, so this is the one of the first things that I'm going to be sharing is a little bit of code specifically for as I build more of my knowledge into the material itself. So for these first 2 videos, it's going to be more on about calcium, but we're going to start with a nice cool introduction to it. So this is specifically for in atoms and molecules in general. So this one is called potassium 40. Potassium in general, it's the thing in bananas, the thing that doctors over exaggerate eat when there are more when there are better ways to get your potassium than a banana. But potassium 40 is one of the 3 isotopes in nature of potassium. Potassium 40 is not what you're typically going to find in nature. Potassium 40 is only at around maybe 0.012% in abundance. It's because it's a relative isotope. It's going to decay into other isotopes, to other, not isotopes, but into other elements or atoms. And the thing about this one is potassium 40, even though it's radioactive, it does have a long half life. A half life is just basically if you have a mountain of something, how long would it for half of it to decay? That's basically what a half life is. So if you had an atom of it, it would take you around 1.2 billion years for it to decay for half of it. So that's quite a lot. And can potassium 40 has many ways of decaying, but the one we're going to focus on today is beta decay. So beta decay is basically when the isotope has a lot of neutrons and not a lot of protons. To stabilize that, because the atom wants to be happy, it doesn't want to be this ball of lump and have to deal with problems. The atom's just like people. We don't want problems. So how do we get rid of it? So what beta decay does, at least in these materials, it converts the neutron into a proton and electron. That's the basics of beta decay. So it has a problem, tries to get rid of it, and that's how it deals with it. In potassium 40, when you go through decay, it has one or two options. We're going to talk about the first option today, second one in this. So the first option goes through argon 40, converts into argon 40. And that's beta plus decay, which is what you're going to see today. Beta plus decay, what it does is the proton electron, but when it happens in the neutron, it's going to convert into a neutrino and a positron. Neutrino is basically this ghost particle. 10 billion of the our fingernails right now, so that's fun. And positron is basically the inverse of an electron. For those who know a little bit about electrons, the charge is an electron, but the charge is inverse. So that's what I've on 40. And that's not common for it to go through beta plus decay. It's more common to go through calcium 40 decay, which is the more related to aerogels, but we'll go a little bit later into that. So potassium 40 decay minus, what that does, it does the inverse of what argon 40 did. So in argon, it gave you a neutrino and a positron. Here it gives you an electron and an antineutrino. So, and that's a lot more stable than having something as a positron, because there will always, I don't know what happened, and we ended up with more electrons than positrons, and that's kind of how it will be. Because if you had a positron and an electron, those are antimatter, and if you combine them, they pretty much equal zero, or in other ways, they annihilate themselves. So that's essentially the behind what you're going to see with the code. And now let's go into a little bit about it. So this is for argon to convert it to argon 40. So I'm trying to understand a little bit about what would happen in the human body, and then as we go into more in depth into the actual aerosol. But this is a good starting point to go. So anyway, we're gonna import a couple just one light for this one. This one located. I'll share it to you guys later. And we're gonna download the import the matplotlib as pyplot, and then the fact that we're gonna use today is that a 70 kilogram man can emit 160, 180 positrons per hour. So this is the beta plus decay in the so think of it as argon 40. As I mentioned, every molecule, every radioactive isotope has problems, so this is their way of dealing with it. So just think of it like that. And for the probability for this to happen, for if you have a K40 isotope and you're trying to make it go into argon 40 instead of calcium 40, the probability of that happening is 10.72%. So that's what you see out the first line of code. And I put this so you can try and understand what's going on here. So I'm trying to make it as easy for you guys as possible. So that's the probability rate. Then we're going to do a time step. So it's basically, we're going to have this per second so you can see how many are a minute of the 160, 180 positrons per hour. So this is by minute, but we're going up per second. And per second, for the potassium 40 atoms that a 70 kilogram man emits, so a big guy, is ironically 3,333 particles. So I don't know, I just found that funny when I found the statistic from the data. And then time, we start from 0, and that we want to go up from 0 to 60. And then the particle list and time was just basically just to store the values, so nothing fancy. And then to make sure that we get the right amount after the end, we want time to be less than or equal to 60. So it must last 60 seconds or 1 minute to see how many of these particles are converting into the argon 40 type, or the positrons. And then that's when we would append and begin to start adding things so that we can see, all right, how does the trend go? And then for the particles, to get rid of as many of the calcium 40 and see how much stored, and then you would multiply the probability and the time step as you keep going up. And then with the time plus time step, you're just basically starting from 0, and then you're trying to add 1, 1, 1, 1, 1 till you get to 60. That's the time plus equals time step. And then the last piece is plotting this thing out. So you'll see in the console layer, just playing around with it. But then you do the pie plot, and then you put on one end the time list, the particle list in R. So R basically that little symbol there, because if you notice here, I was trying to play around with it with some random letters, and basically the reason why R is because it's a recursive. It's a recursive variable, and what it does is it allows for repetition. So it allows you to see, okay, well, it allows you to do the same, the application of this thing as a whole. And then the X label, which is kind of the same, what's the thing on the X-axis, and then what's the thing on the Y-axis. So on the X-axis, you'll see time and then particles. And then SafeFig is going to give you this image that I have right here. Although this is the one where I was playing around with it. I'll show you a little bit of it later. You'll load again. And then SafeFig decay.png, that's the way I wanted it stored. DPI is dots per inch. So essentially what this is, and the reason why because the higher the dot density, you're going to have, what's the word? Like a higher resolution, although that sounds more, but like a higher resolution. But I want to let you guys actually see the graph, so that's why I'm not putting it any more higher. I feel like this is good enough. And then pyplot shows so you actually see what the thing looks like. So now we're going to run. Okay, that's good. Let's see, how do I? So this is 0, where did 0 go? All right, so 0, which is where we started with, 3,333. And then as it goes per second, and then as we have the probability, and then the time step, and then as we were trying to reduce the number of particles, you realize, oh, what did I do? You realize we're going down, so not do that again. You realize we're going down, we keep going down, down, down. And then to the point where all of these actually, each line is basically the remaining of the argon and the calcium, and we keep going down until we get to second 60, or at 1 minute. This is what possibly is the amount of positrons, of actual positrons in potassium 40s that have been emitted. So that's how much. So 63.69, that's the how many of these particles that we started with would actually convert into the positron, or the beta plus decay. So that's for beta plus decay. We're going to go back in a few days, and I'll show you a little bit more focused towards aerogens. This is a good place to start in terms of what we can do with trying to analyze certain things in the body and materials. So we'll be back in a few days and show you a little bit more towards the related to aerogels. But the reason why not in the next few days is I'll be making version 1 of the thing, and hopefully we can keep scaling it up and get to the real version. So catch you soon, guys.